Hello and welcome to EP2CM4, Computational Multiphysics. This is going to be the intro video that goes over how to get some basic stuff working with FlexPDE, and then how to script FlexPDE using Python, and then how to solve advanced dynamics problems including rocket science and fluidic drag force. To start off, we're going to deal with a trajectory problem in FlexPDE. So this is not a problem that you really need FlexPDE to solve, but for illustrative purposes, we're going to solve it with FlexPDE just to remind or maybe inform you how that piece of software works. So here's the problem. Suppose we've got some particle and it's going to start at time 0 with an initial velocity of VI is 21 cos 60 degrees in X and sine 60 degrees in Y is this column vector notation, and an initial position of position vector bold R, bold being vectors, is equal to 0 vector. So starting at the origin, starting at 0, 0 in X and Y. Looks like we're in 2 dimensions by this only having 2 components. So there we go. If the only force acting on the particle after this time is gravity, figure out where and when the particle next has a height of 0 and the trajectory of the particle up to this point. So this velocity is telling us if we're talking about height of 0, if it's next going to have a height of 0, then this has to be the y direction that gravity is acting in. So the question doesn't actually say that, but assume that gravity acts in the negative y direction, and we've got the kind of trajectory problem where we're just looking at it from the side. So x is like the range that it's going, and y is the height. To see the solution to this, if you want to skip to the end, you can just take the code that we've got down here, make a new file in FlexPDE with Control N, and we'll just go maybe make some name for it, 2CM4 vid 1.1, and select all of that, paste in the code that you copied, same code that we copied from the notes here, and then hit Control R, and it's going to run this same code, and you'll see the output here. So you can resize the window to make the plot a little bit easier to see, and what we're plotting here is X in blue and Y in yellow there. So you see we start at 0, 0, and then X increases linearly, and then Y goes up and then down. This is the projectile motion that we've got right here that we planned out. Okay, so rather than doing this, let's just make the code ourselves. So let's make a new value, 1.11 or something. Yeah, new file in FlexPDE, and we'll build it up from scratch, and I'll try and talk you through how this works. Okay, so in this particular setup, we've got an initial velocity of 21, and we've got that's the initial kind of speed, and then it's going in the X direction and the Y direction based on this initial angle. When you make a new FlexPDE file, you start off with just this variable of u, and you can run the default file. It solves nothing. It's by default solving this equation, which is the Laplace equation that we're going to spend time on in week 2, in topic 2 anyway. But for now, we're going to have to change this equation to something different. So first what we need to do is set up the variables we're going to use. And in this case, we're going to use the position and the velocity in X and Y. So we'll do that by saying xd. And because it's a time-dependent simulation, we need to tell it a threshold, which is about how much we care about changes in this parameter. So let's just use a kind of large threshold for now, and then we'll need 3 more variables, x position, y position, and x velocity and y velocity. We can't actually use just X and Y for the X and Y position of this particle, because those are reserved things for positions within the grid in FlexPDE that we'll see later. So I'll try and be as simple as possible for setting this up. In the definition section, you can define whatever variables you like. So let's say theta initial is equal to 60. Now the default is radians for FlexPDE, so we're going to have to convert this from degrees to radians so that the trig functions will will interpret it correctly. So we're going to multiply this by pi over 180. Pi is a reserved thing in Flex, so we're good to type that. It's going to convert 60 degrees to radians. The initial velocity is equal to just 21. And we're going to need some gravitational acceleration in the y direction. In the x direction, there's no acceleration. In the y direction, we've got negative 9.81 as our acceleration. So then in the initial values part, we'll set up the x and y initial value that we had here. So Vx is equal to Vi times cos theta I, and Vy is Vi times sine theta I. Now, we don't actually need to specify these because the default is 0, but just for completion, we'll put in all of the variables that we're solving for in the initial value section. And now the equations is where you put the differential equations you're going to solve. And the DEs that we need to solve here are that the derivative with respect to time, that's this dt syntax of Vy, is Ay. The derivative of Vx is Ax. The derivative of the x position is equal to the x velocity, and the derivative of the y position is equal to the y velocity. Okay, so what we've got here as our equations is basically just laying out that position is the derivative of, whoops, I just realized it's written backwards here. So what we should say is the acceleration is the time derivative of velocity, which itself is the second time derivative of position. So what we'll say is the derivative of velocity is acceleration, and derivative of position is velocity. And writing it like this, we've got 4 first-order differential equations rather than a single vector second-order differential equation. Breaking it up like this allows FlexPDE to solve this thing. So now, all we need to do is specify the time we want to solve it for. And it said until it hits the ground. Not really sure how long it's going to take to hit the ground, so let's just use, I don't know, 20 seconds here. And what we'll do under the plots part, we don't need monitors. That's monitors are if you want to watch the simulation while it's happening, but we're just going to wait till it's totally done and then plot it for all time. So we'll say for t equals 0 by 1 to n time, so 1 second spacing on this final plot, and then we'll put in a history plot, which is the one you use for a time-dependent simulation. History yd at 0, 0 versus xt. So this at 0, 0 stuff refers to in the grid, and it has in the mesh that we're solving this simulation on. It's something that's going to become more clear next week when we're actually using finite element method. For now, just it's going to be there every time. This is where we're evaluating the value of the thing we're solving. So, yes. What we didn't do this time is include a halt condition. So we just let this continue going and we ended up with this very negative height. So let's specify this in our time range, 0 to 20, halt, if ever yd is less than 0. And now it runs for a short amount of time and then stops. Now, now that we've got this plotted out, I can explain a little bit what this at 0, 0 thing means in the history plot. That's where in the grid we're actually evaluating the solution. So none of the stuff that we were doing was actually space dependent, right? We're not actually solving the acceleration of this particle doesn't depend on where within the particle we're talking about. So every part of it has the same acceleration, so we didn't actually need any dependence on space there. Some different differential equations will be derivatives with respect to space, and then we'll have to look at that grid. But for now, with only derivatives of something with respect to time and nothing depending on derivatives of space, then you don't actually need that mesh. So it's really just slowing things down to evaluate it at this many points. So a trick is, under the method controls here at the top, select, put in ngrid is equal to 1, and this is going to make it an imprecise mesh, and it'll be faster. We can't even see it run. It's so much faster there. So check that out for yourself. See if you can get that simulation to work as a start. All right, phase 2 is going to be scripting these FlexPDE programs using Python. So to do this, we're going to do 5 different steps. How to edit a text file in Python, how to have Python run some external command, how to have FlexPDE run from the command line, how to have FlexPDE export results in a way that an external program can understand it, and then how to have Python read results in from the format that FlexPDE has exported them so that we can process them in Python and maybe plot them there. Why you would want to do this is to be able to run a trajectory program a whole bunch of different times. So if you're feeling like, all right, I don't see the motivation to automate this FlexPDE thing. I mean, Flex is so fast. We just hit run and it does the simulation. The motivation is if you want to do a whole bunch of different simulations all at once. So imagine that you want to have a plot superimposed for all the different possible launch angles between 5 and 90 degrees in steps of 5, like this. So this is the sort of thing where you really want a scripting program external to FlexPDE to be able to load up those simulations and run them. So that's the motivation for doing this section. So the first step in here is editing a file from within Python. So first, we're going to need some Python. And if you don't have Python installed, then you're going to want to get that taken care of right away so that you can play along with this. Seriously, pause the video, go click on this link, get Python. If you're not sure what to get, then just go with the Anaconda distribution. It's pretty great. I like it. That's the one that I prefer right now. If you've got your own, then that's fine too. I'll wait. All right, so I'm assuming that you went and did that. You've got Python installed, and everything's good to go. Let's just load up Python here. So we've got the Anaconda navigator here, and what you want to do is click on Spider from within that. And this is going to launch an integrated development environment that we're going to use to be coding Python. So we've got Spider loaded, and we've got a new file in a working directory which is not cloud synchronizing. That seems like it can mess with what's going on with FlexPDE, so that'll be important for later. What we're going to be doing in here is, first of all, just making sure that we understand how text editing works in Python, and like editing strings and all that, and then outputting things to the outputting edited files. We need to do this because our FlexPDE file is going to be in text format. So the way that we're going to actually output this file at the end, once our example is totally done, is with saving the Flex file as a string within our Python script, editing it, and then exporting that. So I think I didn't copy the full piece of the code and I missed the import libraries. Very important to keep those. Yeah, okay. So, and Spider was indicating that with those warnings there, by the way. So in case we get rid of that, then you see it is highlighting things. So it's saying undefined name SP, undefined name. We don't know what subprocess is. And that's because I'd gotten rid of the code that was importing those. So once we have those back in there, then the warnings go away. This is one of the advantages of using an integrated development environment. It highlights some of these errors before you even get to compiling the code or running it or any of that. You can tell right away if you've maybe typed something wrong right when you've typed it. Okay, so once we've got everything in here, how this program works that we're going to build up is we've got a string which has all the code of that FlexPDE is going to run. We're going to save that file, and then we're going to tell Python to tell FlexPDE to run it. Flex outputs the file outputs a text file that we can then read in Python and plot. So this is going to do it for all the angles in the range of 5 to 91. Let's see if it works. Seems good. Okay, and there's that plot. All right, let's build this up in stages. So first thing we're going to need is some text editing stuff. To experiment with the text editing in Python, what we want to do is test out things. So first we're going to need to know how to get output from Python. So that's with the print statement. Print maybe heyo enclosed in quotes there, and we can hit F5 to run, and there we go. So it's run the file here. We've got heyo printed out. A string like this, if we put a new line, then it's not going to work. So this is a syntax error. But if you enclose it in triple quotes, then you can include new lines. It'll include all sorts of other characters, like whatever you want in there, and it'll print out the whole thing. It just interprets everything in there literally as a string, with a couple of exceptions or some special characters that you can put inside of this thing if you want to edit it. So an example of this is %s. If you put %s anywhere in this, let's just throw it even right into the middle there, %s, then afterwards we can put % and put in another string, heyo, and now the %s inside this one will be replaced with what we put after the % symbol outside there. So this is useful. This is something that we're going to be using to edit a string. Let's do it with a variable. So imagine we've got my string is equal to let's go let estero, and we wanted to maybe let we want to give different options for what to put after this thing. So we'll put %s there, and then we'll say print my string %estero, or if you want to be more predictable, then you can say s go, like that, ''s, and there we go. So you can be saying let's go let estero, or let's go, right? So that's the editing of strings using the % syntax. You can have multiple percents inside the same thing. %s is the best %s around. And then what you need to do is send this multiple strings. So we're going to need a couple of strings here. So we can go, I think in this format, A is the best B around. Yeah, that's right. So we just need a bracket to enclose the different arguments that we're passing to this % notation here. The %s notation is the one that we're going to use for FlexPDE, but for most other situations, this is a little bit awkward for editing strings. So in general Python programming, it's probably a little bit more convenient for you to put something like this, name 1 is the best P around, and then you can use .format, and whatever you typed in there as your inside the curly brackets can now be used as a variable. Name 1 equals A, and then the second one, P equals, you can put like a number, you can put another string. Let's just show a number here. There, so it works the same. What's nice about this format thing is if you have a big list of things you're replacing with the %s method, then it's a little bit, it can become hard to read, right? Like you have to figure out where was the first %s, whereas this one you say, okay, where's name 1 in there? You can double click on it and it'll find name1 in this string. You don't have to have them in order. We could have specified P equals B here before we specified name1, and it'll work totally the same. It's not confused about which one is which based on when we set it. So that's some string manipulation in Python. There's definitely a lot more that you can do with this. Maybe a little bit of a taste to get you excited about some of this. Name1, is it defined afterwards? No, it's not. So if you say print name1, then it doesn't show up. Even though we set up here name1 equals A, in another programming language, anytime you have this is an assignment statement. So in C, if you put this somewhere, now you've assigned name1 to A. In Python, though, we actually are not doing that here. This is like a local variable that just exists for this one format string. In fact, you can even do some pretty funky stuff. So let's imagine we say x is equal to 7, y is equal to 2, print, we're gonna use a format string that happens to have the value of x that happens to have an x in it, and then we go format and we say x equals x. All right, can we do this? We already used the name x. What do you think this is going to print? It works fine. It says the value of x is 7. It's not confused about that. What if we say the value of x is y? Well, it'll work totally fine. It prints out the 2 for there. Now, when we did this, did we reassign x? Print x. No, we did not. So you can even say funky things like this. You can reuse the same variable name in this thing and then substitute it in afterwards. Totally fine. It's a local variable, not confused if you use x equals y and reassigning it, or even if you use x equals x, it's interpreted as a different variable in here than this one. So this x, confusingly, is a totally different thing than this x. This is the one from externally that we're pulling in. This is the local one for that format string. Lots of nuance. Definitely good to test out how code works when you're checking something like this with these simple little programs, just to make sure that you're on the right track and things are working the way you think. So the other part of the first thing that we need to do is understand how to export these strings to files. So what we're going to do is review the file input-output syntax in Python. And this is written at the end of this thing. It's in this example code here. I'll see if you can find it with a scavenger hunt. There's also a video on how to do this in Python, along with a lot of other really cool things in Python by this channel that I really enjoy, Socratica. So they're definitely something to check out. See if you like it. Probably, if you're just here for a Python video, you should probably go watch this instead. If you're not in the Computational Multiphysics class and you don't care about the solving of differential equations. If you just want to know how Python input-output works and you found your way here somehow, then I am so sorry. Please click this link instead, or just look up Socratica file input-output on Python, and then you'll be in much better shape. But for the rest of you students here that are stuck because you also want to learn about how to script FlexPDE, then let's continue. So file input-output, what we'll do is we will get a folder open on the computer, and we'll go to temp Python scratch files. Yeah, this is the folder that we're working in right now. You can actually see a bunch of stuff that was created before by running this this example code when we ran that. For now, though, what we're going to do is practice making some files and seeing that they appear over there. So here's how this file input-output works. With open, and then we're going to put in a file name right here, new files.txt, in write mode as whatever you want to call it, as F, and then we're going to say print, just a regular old print statement like we were printing up here. You can use any of these things. with the exception that you give print another argument, not just the first thing, the thing that you're printing, but you give it a second argument that we're going to print to a file. File equals this same file f. Now what's nice about this with open is as soon as this thing is done, it automatically handles closing the file so that it's not in use, and we can open it with some other program. So we run this. And it didn't output anything because we didn't tell it to, so there's no output to the screen, but it did make this new files.txt, which hopefully should contain the value of x is 7 right now. Yeah, okay, here we go. The value of x is 7. There's our new files output. Fantastic. So now we would be able to use this to output some FlexPDE code. So that's the first step completed. All we need to do is enter the FlexPDE code in this big multi-line string, possibly using %s anywhere that we want to replace a variable in case we're going to run this same code multiple times, and then print it to a file, and then it'll be in the file for FlexPDE to open and run. Stage 1 complete. Phase 2 is how do we run an external command from within Python. So we're going to need to do this if we want Python to be opening up Flex and having Flex run some stuff and output some stuff from that Flex file. So to do this, we need to use the subprocess library. So we're going to import subprocess, and then we can say subprocess.run, and then run whatever command we like. So we'll put some command in here. Now, as a way to test this, that this is working, we're going to go in this folder here where we just made this new files.txt thing that's all beautiful and all that. And just as an example, we'll get rid of the part of the code that was making that, and we'll just say subprocess.run del new files.txt. Now this is probably not going to work for you. So it gives you an error that it can't find the file specified. I'm not 100% sure. So if you have a better explanation for what's going on with this than the one here, please let me know, or even if you can confirm this. I think the reason this doesn't work is because we haven't set shell equals to true, and delete is a shell command. So it's not actually complaining that it can't find new files.txt. It's complaining that it doesn't really know what del is, if I'm understanding this right. Anyway, when you do this, it doesn't complain, and new files.txt has disappeared. If we run this same thing again, it doesn't complain. Weirdly, when you put shell equals true, it doesn't tell you about a lot of this output that happened. There's no complaint about this command. It just went and executes it. So it seems like it all works like that. So you can try this out and let me know if you have similar results. Okay, phase 3, how to use FlexPDE 6 or 7 from the command prompt. It's going to be almost the same command if it's FlexPDE 7, just it'll be a 7 instead of a 6s there. So if you're using a version that, if you're using a different version, then just update the command accordingly. Okay, so the way that we're going to do this is first get somewhere where there is a FlexPDE file, and then try to run it from the command line. So first we'll get some FlexPDE code, and we'll make a new FlexPDE file, maybe in this temporary directory. So we could make a new file and then just paste the code in there and all that, and that's, you know, fine. But now we've got a much cooler way to do this, right? So we can just go right into Python and make the code a multi-line string. Flex code is equal to this, and there's the code. And now we're going to output this to a file. So we're going to say with open flexin.pde for write as f. We're going to print flex code, I think we called it. Yeah, print flex code to that file. We won't be needing these other examples for now, so they're just cluttering things up. Let's get rid of that. And there we go. So let's check if this works. flexin.pde, and we can open that up and run. That's the same file that we were running earlier. Okay, so that's good. We've got this thing. When you run Flex, you'll notice that it creates this output file. So we can delete this, run it, and there we go. The output file shows up when we run it. So if you delete the file again, then we'll know if we've actually run this from the command line. So let's do just that. We'll go import subprocess, subprocess.run, except instead of this this other thing we were running here, we'll run the command to run FlexPDE from the command line. And the command to run FlexPDE is FlexPDE 6S or possibly 7, and then you give it a run mode. So let's just do silent mode, and then we'll put in the file that we called it, which is flexin.pde. That's what you do. So you do this whole thing, and it's going to run FlexPDE in the background in silent mode without interrupting anybody. And we'll know whether or not that's worked by if we see this .pg6 file show up here after we run this Python script. So let's see. Aha. There it is. We have successfully run this file. Now, to really get some useful output from this, we're going to need to modify we're going to need to learn how to get Flex to actually output data in a way that we can then import in Python. So there's a little bit more work to do, but that's the first step of this thing. The next sort of little wrinkle on this before we leave this is oftentimes it's more convenient, rather than just having it as a single command in brackets here, a single command in a single string, it's nice to have it broken up into different parts. So we might be able to say maybe flex file name is equal to this flexin.pde. So it's a little bit more descriptive, and then we'll put that same variable here and down here as well. So how do we put it here? Well, what we want to do is give a command in a list. We can pass a list as separate strings to give the subprocess, and it will execute this command with this directive with this as the next argument. So we can just give a list of arguments to subprocesses run command rather than a single literal command to run, and it will run this as well. So this should accomplish the same thing as we just did. And there we go. Yeah, so that is another way to run flexin.pde by just specifying the 3 different arguments we were giving to the command line as a list of arguments passed to the subprocess library's run command. One other thing to mention is that the FlexPDE 6S command will not, or the FlexPDE 7 command will not work unless you give it the full path, which is c:// FlexPDE 6 student / FlexPDE 6S on my system here. So you can see if you go this FlexPDE 6 student, and that's where your FlexPDE file is stored by default, right? FlexPDE6s.exe, that's what this is accessing. The reason that I didn't need to put that before is because I've added it to the path variable. So a path variable says anytime you execute a command from the command line, so you get like a terminal here, FlexPDE 6S, and then we can type something after it, or it'll just launch it. So even though we don't have it installed in this users mdmin directory, it's going to launch it anyway because it knows where to find it, because this looks not just in the current directory but also everywhere everywhere specified by your path variable. To see your path variable, go to Advanced System Settings and look at Environment Variables, and then look at the path variable here. You can double click on it, or if it isn't there, you go new and you add something called path, exactly like that, special name of a variable in Windows, and then just add FlexPDE 6 student. So it also will look in user profile, app data, local Microsoft Windows apps, and it'll look in FlexPDE 6 student anytime you try and run something from the command line. In Mac, it's a little bit different, but whether in Windows or Mac, there's a list of instructions here that you can check out, just in case you've lost your file and you just have the video. Here's the Mac instructions. Next, how do we get Flex to output data rather than just plotting it as a history graph? Well, the way that we do that is by editing the history graph syntax to, after the graph, after the plot, say print only export with a format string like this, and then a file name that we want to export it to. So this means the time, B is the tab in this format string, number 1 is the first variable in that list, and then another tab, and then number 2 is the second variable in that list. So if we go to the file here, the Python file, and the string in here where we had this history plot, rather than making the history plot y versus x, if we make the history plot xd yd at 0 0 print only export format this thing, we don't need this one in Flex, so we can comment that out. Comment in Flex, remember, is the exclamation mark. Now it should create a file, test.txt, and that should be filled with the data points from this file. Data points from this trajectory that we had. So we just got this other version of it over here. And remember that we start off at 0 0, and then we move up in y to a little bit above 15, maybe 16 something. And we go from x 0 to 40. Y goes up to 16, back down to 0. X goes 0 to 40. So let's go to this folder here. We've actually already got test.txt created by this other Flex program that we were running. So you can see the format of this thing. Rather than overwriting that, let's make vid1 flexin.txt, flexin output.txt. Yeah. And let's see if we get that. Okay, so not only indicated by the flexin.pg6, but also the text file showing up. And here should be the data that we've got, that we were plotting with that other script here. So this is exactly the same Flex file. It's just that we're now outputting in a long, outputting the raw data that was output by that Flex file, rather than plotting it on the screen. Okay, so that's how you get Flex to output its data in a format that Python can read in. So since this format of the file has a bunch of headers and then tab separated data, we can quickly get this into an array in Python using the SciPy library. So let's not just import subprocess, but import SciPy as SP. That's a pretty typical thing to do. And now what we're going to do is try to open this output file and read in its data using something from SciPy. So we are going to use something similar to this, except instead of opening it in write mode, we're going to open it in read mode. Again, as F is okay. And instead of print this, we're going to go import it into something called data. Data is equal to, this is, well, let's say file or flex output raw data is equal to sp.load, I think it's sp.load text, and then give the file name, which was vid1 flexin output dot text. And then let's see, what else do we need for sp.load text? Maybe skip rows. Skip rows equals 7. So seemed good. Let's see what we have in that now. Okay, check it out. We've got an array, a multi-dimensional array, which is the same data that was in that file. So vid1 flex and output, we have now input it into an array format in Python that we can now manipulate with some other program stuff by using the regular array methods in Python, which are exactly the same as the ones in MATLAB. So for instance, we could say t is equal to flex output raw data, all rows and 0th column. xd is equal to flex output raw data, all rows and first column, and yd is equal to flex output raw data, all rows and second column. And now we've got the times just as the first entry, we got the times in the time variable, xd as the xd saved from the second column, and yd saved from the third column there. So now that that's the case, we can plot it. So we're going to import matplotlib.pyplot, pyplot, I think, as plt. And now we can say plot.plot xd yd and plot.show. Pyplot. There we go. Okay, so it is spelled right here. People just generally call it something incorrectly spelled. So that's where the PLT was. So import matplotlib.pyplot as plut, and then plut.plot xdyd plut.show is a thing that's going to make the plot actually show up there. There we go. There's a lot more fun things that we can do. Give this example a shot just to make sure that you've got it. Got this locked down, and you can make this Python scripting of our basic trajectory file work. All right, at this point, if this is as far as you take it, then there really wasn't much point in using Python, because we got this trajectory already. It just was a lot more work to do to kind of write the code in Flex, get it working there, and then go all the way over to like switch from this Flex file, where we had the answer already, go into Python, and then do this whole thing to get it to work. Now, the real advantage is in scripting this, so that now that we've got a basic script, we can use the looping power of Python and all the processing power that it has to run this thing a whole bunch of different times. So here's how we might do this. First, we're going to make something that we're going to replace here in the string, say the initial angle. And then what we can do is we can say that we're not going to print just flex code, but print flex code angle maybe 60, just to test that this works. Let's see if we get the exact same plot. Yep, looks good. What if we do 45? Yeah, it is different. Notice that 45, now we went past 40. If we do just 20, it's a little bit hard to tell because it's scaling the plot, but now we went to a shorter distance. It didn't go up as high as it did did here at 45. Actually went higher at 60, and that's not surprising. Higher launch angle means it's going to go higher, but doesn't end up going quite as far. Okay, so what we want to do is take this whole thing that we need to run every time and put it all in a loop. The actual process here is to open the file and print the flex code, run the command, open the output file and import it, and then get the data from that, and then plot the data that we just read in there. Okay, so we actually can put this stuff back here. What we'll do is we'll take this whole thing and we'll loop over it for different angles. And the way that we're going to do this is with the arange command. Before we do that, let's just explore what this does. So print, let's say y. We're going to go y is equal to A range. How to explain this? So if we go y is equal to sp dot a range, then we give it a start, a stop, and a step. So if we go 0, well, let's imagine we go 5, 85, 5. Okay, so starting at 5 up to 85, steps of 5. If we print that, it's going to print out all the different data points. Notice not including 85. So up to but not including this thing. If we want to get 85 in there, we have to go to 86. And now we've got our 85 in it. Unlike last time, we've got a number that's bigger than 85. We could go all the way up to 90 here, and it'll just end at 85 there for the last entry in that list. Okay, cool. So now what we want to do is we're going to say angles is equal to sp.a range of 5, 90, and 5. And then for angle in angles, we're going to do this thing with open, and then we're going to replace it not with 20, but with that angle that's in that list. The other thing is we don't actually want to show the plot every time. We're going to wait till we've got a bunch of those things plotted and then show it. Now this is going to take a moment to run all those different files, but once it's done, we've got everything plotted. So there we go. We've looped over it by having an iterator, angles, that's going to go through this, all the different angles in the loop and be equal to the different values in this thing while it's going through that loop, and then rerun the code for all of those different possible angles, replacing the thing in the flex file, output a file that gets overwritten. It still is just rewriting this exact same file every time. If you wanted to, you could make it output a separate file rather than just overwrite the same file. Totally fine. And then is going to and then after that, we import it, we plot the data, and we finally show the plot at the end. We can get a little bit more fancy with the plot by adding in X labels, Y labels, and legends. So we only need to set the labels at the end. Plot.x label is equal to X displacement in meters, say. And let's see if that does something different. Ooh, this is a little bit slow at this point because we're doing it a bunch of different times. So maybe I shouldn't test quite as often, or should lower the angle range while we're going to be messing with this. Let's go 5 to 11. We're just going to get 2 in there. Okay, so the X displacement there, and then the Y label will be Y displacement in meters, and that should show up on the vertical there. Okay, beautiful. And now we can also add in a legend. There's a couple of different ways to do that. The first one is just plot.legend and then put in the angle range. Angles that we had in the array, and let's see how this works. Yeah, so we've got 5 and 10. The same order that we gave it will be labeled there. That's a simple way to do it. Another way to do it is under the is something that I just found in the legend guide under the matplotlib documentation. So when we plot the data originally, we can give it a label. So we can go label is equal to angle, and then here we probably don't need to give any argument to legend. Yeah, so if we label all the plots while we're plotting them, then we can just say have a legend, and then it'll show the legend afterwards. We don't have to re-give it the angle range there. So a couple of different options for how you might have a legend incorporated into your plot. Let's go back to the large amount of angles there and just see what this looks like. And there we go. So it's running off the page. We've got so many different data points plotted that the legend doesn't even fit, which is why you might want to explore some of the other options here for how to lay the legend out, maybe outside the plot, maybe on top, that kind of thing. Lots of different options that you might consider exploring in the documentation. Rather than messing around with the legend, I'm going to do something else here, which is include fix the issue that this takes a while and we've got no output while the individual sims are happening by making a print happen after we've imported data successfully. So right in this step, after we've got the data into XD, we can print and we'll use that second format, angle, and we'll put in a degree symbol here. So this is capital N, is that it? Degree symbol. No, that's not it. Here's how you find out what it is. You go and you Google Python degree symbol, and you go to Stack Overflow, and you look for the one with the most upvotes. Here's a short answer, /n degree sign, and there we go. And now you know a lot more about programming. Here's the programmer's hidden stuff. Let's get that out of the way so the boss doesn't see. Now we go back to this. We get angle /n degree sign, not symbol. And so this is going to output, we're going to have the angle, degrees, landed after that seconds, t seconds, at that x equals this meters. Okay. And now we can format this thing. Dot format. Angle equals angle. What else do we need? T equals the last thing in the time list. So we're going to go T -1 by putting -1 as the index that we're getting. We'll get the last element in the array. And we can also do this for x. X equals xd -1. Note that it's totally fine if we're using the same variable here as we had later, as we're calling later, or as we have in our program. It's a temporary thing that's only interpreted from within this list. So this should now, if I hadn't made any mistakes, output the angle that we used and a nice degree sign, and then say that it landed after however many seconds at the final position that it had. Let's check. Okay, there we go. So 5 degrees landed after this, at that, 10, 15, 20, 25, and it looks like it stopped after that. That's a little bit surprising. So if, although this is illustrative, if the program is ever stuck somehow, then what you can do is hit the stop button there, or hit Control-C to terminate it, and then just try again. Sometimes it might even do this, where it's totally crashed and completely refuses to run anymore. Then we can try to terminate the console. You can, there we go. It takes a moment and now it's restarted, and now we can run it again. So something seems fishy suddenly around this this 30-degree simulation. So we'll cancel it again. Try to close the file, get it to restart here. Yes, what could be happening? Well, it's possible that FlexPDE is getting hung up. So in the sub-process run, we'll give it a timeout and say, if it takes more than 5 seconds, then stop. All right, so sure enough, we didn't end up needing it anymore, so it's unclear whether that was the issue. The next thing to fix was going to be in here to delete the PG6 file. That gives a memory to Flex of how it ran the simulation the last time, and might be giving it the wrong impression about how that thing works. Although it yeah, so it's possible with the PG6 file it was using from the 85, it ended up with a slightly different answer for the 5, and then that led to a different one for the 10, etc. And when it was getting to that that one in 25, it ended up with something slightly different. So now, because we deleted that, we might see slightly different answers here when we run this again. Or maybe we caused the thing to suddenly crash. So the timeout expired, but fortunately this stopped the thing from totally crashing. Unclear why it was sometimes timing out there. But with that timeout command, you can just make it work again, and you're good to go. All right, next part is how do we do some advanced dynamics problems? Like, this problem's all well and good, and it's great that FlexPDE does it. But, I mean, a projectile problem like this has an analytic solution. We don't need to use a finite element method solver to deal with this. So let's deal with some more complicated problems that are much more difficult to solve analytically. We're going to do two. We're going to do rocket science, and we're going to do fluidic drag force. So some rocket science stuff. The basic idea of a rocket is that it's difficult because the mass is changing. So imagine that you've got something which is changing mass with time. So we've got it's expelling fuel backwards at a rate of q in dm by dt, q equaling negative the rate of change of the mass of the rocket with respect to time, and because of this, it's giving this very difficult problem to solve analytically, right? So imagine if the mass is not a constant, then the acceleration is a constant. You can't use your kinematic equations anymore, and you're going to have to do some integrals in order to get it to solve. So what we're going to do is do kind of a complicated example with the fuel expelling by modifying this projectile problem, so we can kind of see how it affects things with the trajectories right away. So what we'll do is we'll imagine we've got that this thing is not just a projectile, but it is a rocket. So we still launch with 21, but now we've got a mass on this thing. So let's add in the stats for this this V3 rocket from later on in the examples here. The very last example is this V3 rocket from Red Alert 2, and this has a mass of 800 kilograms, which is 80% fuel. So let's go with mass initial is equal to 800, and the fuel initial mass, MFI, is equal to 0.8 times the initial mass. We could talk about the mass of the rest of the rocket. Mass of the rocket, not fuel, is equal to whatever's left. So that would be the initial mass minus the fuel mass. Yeah. Now, because it's expelling fuel, the fuel changes mass with time. So the mass of the fuel is equal to MFI minus Q times time. So if we're expelling at a rate of Q, then it's going to be decreasing in time proportional to Q times T. We'll also need to put in what the fuel expulsion rate is. So we can just subtract Q times T because the fuel is expelling at a constant rate, which is 40 kilograms per second. And so the mass of the fuel is equal to this. However, there's a problem. This function eventually is going to become negative, which says we've got negative fuel mass. So that doesn't make sense. We need something which is never going to be negative. And to do that, we need to figure out how long we have fuel for, and that'll be T fuel. So time that we have fuel for would be the initial fuel mass divided by Q. Why is that? Well, we've got, imagine we've got 40 kilograms of fuel, and we're expelling it at 4 or let's just use a real number here. Imagine we've got 40 kilograms of fuel and we're expelling it at 40 kilograms a second. It lasts 1 second. What if we've got 400 kilograms of fuel and we're expelling at 40 kilograms a second? It's going to last 10 seconds. How did you get that? You divided the 400 by the 40. So the time that we have fuel for is equal to the mass of the fuel divided by the rate of fuel that we're expelling. So this is kilograms of fuel divided by kilograms of fuel per second, and the dividing by seconds is going to invert. So kilograms over kilograms per second is going to give us the second. This is the time that we have fuel for. Okay, so since that's the time we have fuel for, we can specify the mass of the fuel. Depends on whether the time is past this time. So we can say if T is less than T fuel, then this, else 0. Cool. Now this accounts for the changing mass, and that's not going to do anything because we're just saying the acceleration is entirely based on gravity. To make this a little more interesting and add in the complication of dealing with this changing mass, we have to also add in the fact that this mass being expelled backwards causes a thrust force. So conservation of momentum says that if the fuel is being expelled backwards at 1,000 meters per second relative to the rocket at a rate of 40 kilograms per second, that's a rate of momentum leaving of 40 kilograms times 1,000 meters per second. So the mass times the velocity, and then that thing creates a momentum of all the different fuel leaving. And if 40 kilograms of that per second is leaving, then that's a rate of change of momentum of the rocket and fuel combination in the backwards direction, which means the rocket itself has to have that same rate of change of momentum in the forward direction, and that's the force. So force is equal to change of momentum with respect to time, and the momentum is the Q of the fuel times the V of the fuel. So, or really the mass of the fuel that's expelled in a given time. So that's how we get, for constant fuel velocity, that it's just dm fuel by dt, which is Q fuel. Okay, so there's the force that that rocket propulsion is putting back on the rocket. And we can incorporate that into our code here by saying that the thrust force is equal to, again, if we still have fuel, then Q times V fuel, and we'll have to put in what that is. V fuel is given as 1,000 in the question, else 0. Okay, now which way does that thrust force point? Well, this is complicated. It points away. It points in the direction the fuel is leaving the rocket. And for this particular rocket, it makes it kind of convenient because we don't have to keep track of the rocket angle. We're told that the fuel always provides a thrust force in the direction that the rocket is moving. So the thrust force is always applied in the direction of its instantaneous velocity. So we just need to figure out what that direction is and put the thrust force in that direction. Here's how we'll do that. We've got the velocity variables vx, vy. So we'll form a unit vector that points in the direction of velocity, and then say that the thrust force in the x direction is equal to the thrust force times the x component of that unit vector. Component of velocity unit vector, right? And then we'll do the same thing for y. So what is that unit vector for velocity? Well, we'll form the magnitude of velocity, and then we'll say that ftx is ft times vx over v, because that'll be the unit vector for velocity. Yeah? So velocity is equal to whoops, yeah, Vx and Vy. And the magnitude of velocity is the root of Vx squared plus Vy squared. So therefore V hat, which is V over its magnitude, would have components of Vx over V and Vy over V, where we can substitute in what the V is by just finding it there. And so there we have it. This will be the x component of the thrust force, the magnitude of the thrust force times Vx over V. Same thing for y. Fty is equal to Ft times Vy over V. And now we'll add these to our acceleration. So acceleration is the force divided by the mass. I don't actually have that written down. Oh yeah, here we go. M times V dot is equal to this thing. So this is acceleration. So if we want the acceleration, we just take the force that we've got and divide by the mass. So AX will be FTX over M, and AY will be FTY over M, minus 9.81, because we've got the gravity acceleration applied as well. The other thing is we need to figure out what the total mass is. So we figured out what the fuel mass is. The rocket mass, M, will be equal to the fuel mass plus the mass of the rocket that isn't fuel. Okay, so let's see what happens differently. Wow. Well, it didn't land. It just kept going. We've moved 14 kilometers so far. Let's increase the time. So we've got maybe 2,000, and we don't want to go in steps of 1 because that might take too long. So let's say n time over 100. So it still actually looks a lot like a projectile motion. The difference is that it went much further. So it didn't go like 40 meters, but it went 200,000 meters, right? 20 E4, so like 2 E5. So this is way further. It looks like it went up by like 40 kilometers here. So at these altitudes, we might have had to start paying attention to some different effects on this rocket. Probably we need to deal with the fact that this is not going to have just a little g of acceleration at these altitudes. The air is going to be quite complicated, but for now we're going to ignore that and say, yep, this is basically the rocket thrust force, while other complications could show up, like maybe G no longer works at this altitude and we need to include drag as well. This is how you deal with the rocket thrust force. One other thing that we can do to kind of show that this is doing something that isn't just like a regular projectile is have a look at what the acceleration is doing. So we'll change the time to 300 because the 2000 was just a little bit long, and this shows it in a little bit more detail. It makes the plot go a little bit slower at the start. Another thing we'll do is we'll add in a history plot of AX and AY at 0, 0 to look at what the acceleration is. So here's our acceleration plot, and you see that the acceleration in, let's say, X is increasing with time from a couple of effects. The mass is decreasing here, and also the rocket is pointing more and more in the X direction as it starts to tilt over from its initial point. The Y acceleration also increasing in time because of that decrease in the mass. And then after we run out of fuel, a very sharp boom drop down. No more X acceleration. Y acceleration is just negative G at that point. So this is another thing that you can do to verify that it is actually working as a rocket. Next up is going to be incorporating fluidic drag into this. So to deal with fluidic drag, what we do is we add in this equation. So for things that are moving very slow, you can use linear fluidic drag and say that the drag force is proportional to the velocity linearly with some drag coefficient there. This is okay for small objects or very slow speeds, but most of the time it's actually better modeled by this equation. This equation still works for those other relationships. It's just that the drag coefficient is no longer a constant. It's most useful when drag coefficient is reasonably well behaved with increasing velocity. And that tends to be the case for things that are about our size. So drag force is half rho, this is air density, times CD, drag coefficient, times the frontal area, which you have to define whenever you define the drag coefficient that you're talking about. So what drag coefficient you get will depend on what area you chose to use for your definition. You do the experiment and you get the same force on the object, regardless of whether you say that the area is the total surface area of this sphere or is just the shadow of the surface area when you look at it from the front. That's what frontal surface area is. It'll be the same force either way, but you'll, if you're expecting to use a different area in this equation, you'll have a different coefficient accompanying that depending on your definition. So you just need to be consistent. And then velocity squared. So this is the speed of the fluid that's moving past it. So here's some examples. A smooth cylinder has a drag coefficient versus what's called Reynolds number, which is the ratio of inertial to viscous effects in a fluid. So this is fluid density times, again, arbitrary length scale, just like the arbitrary area here. Velocity divided by the dynamic viscosity, kind of like the stickiness of the fluid. So increasing largeness or fastness for a given fluid will make the Reynolds number go up, and that tends to make drag coefficient get towards this different regime. This is the onset of turbulence, if you're wondering what this behavior is over here. So we've got some decreasing drag coefficients with increasing Reynolds number, then it's mostly constant for this region. This is where we're assuming that we are, which tends to be things around our size. Up in the turbulent regime, although it dips here, it's reasonably well behaved again over there. So it's only if you're in these really low Reynolds number regimes where you'd be better off using a linear drag coefficient relationship. So what we've got then is quadratic damping, and that means we're going to incorporate this as our drag force. Now, the V3 rocket that we just did told us in the question what the drag coefficient was, what corresponding area to use, and it did not tell us what the air density is. So we're just going to make some reasonable assumption on the air density in order to answer this question. So we'll do that in the answer and just see if it affects things very much. So let's check. We've got our final position, which for our launch angle of 60 degrees, we can report what the final position is. Value XD at, I think it's something like this. Report val XD at 0, 0. Yeah, so there's our final position, 232,450.9 meters. With the precision that we're using for the simulation, those are not all significant. But anyway, yeah, that's how far it's going. So now what we'll do is we'll incorporate that drag force. So CD is equal to 0.05 and A is equal to 0.8, and we'll write out the drag force. So we'll need an air density. Rho air is equal to, let's say, 1.3 kilograms per cubic meter. And similar to writing the the thrust force, drag force is equal to 0.5 times rho CD times A times this velocity that we just calculated squared. And we really need an x and y component to it. So FDX is equal to FD times Vx over v, except that points in the negative direction. So the drag force points negative the direction, the velocity of the rocket relative to the fluid that it's in. Because if we're moving through the fluid in the positive x direction, the drag force on the rocket is going to be in the negative x direction. So that's where that negative comes from. And then Fdy is equal to negative Ft times Vy over v. So we'll just add these to the forces before we divide out the mass there, and see if it makes much of a difference. So before we again had 232,000 meters as our final distance. Oh, I didn't call it rho, I called it rho air. Yeah, so that's quite a lot of difference in the final range there. Only 20,000 meters for this range once we've got this this fluidic drag there. So you can see it really slowing things down. When we've got a lot of x velocity, it says, nope, slow that down, and a lot of y velocity gets slowed down as well, but the acceleration from gravity eventually just has us still going back down towards the Earth. We also have extra acceleration terms here. So even after we've run out of fuel, which is at this sharp line right here, the drag force is really slowing us down, and that's this strong negative effect on the acceleration right here, the strong negative acceleration slowing us down. Okay, so that's the trajectory for 60 degrees, and 45 degrees looks something like that. Now with this complicated thing, we might wonder whether 45 or 60 degrees or 90 degrees is the optimum. And so with this drag force incorporated and this rocket thrust incorporated, it's time to go back to our flex file, our Python automated flex file that is, and see if we can modify things. Okay, so we'll take, all we really need to change is the definitions here in the flex file. So in fact, we'll even keep the angle stuff the same. We'll modify all of this to be this much more complicated nonlinear stuff that we put in with Rocketry and Fluidic drag. And the other thing, I guess, actually, we need to make the time go a lot more than we had before. So we'll put the time up to a possible 300. And to make it not take forever, we'll go time equals 0 by n time over 100. So we only get 100 time steps, no matter how long it ends up taking. Okay, let's see. So we've got these much larger ranges in there. It looks like we've got some trajectories similar to what we were seeing in the flex code. And it also looks like the optimum is maybe around 50 degrees rather than 45. So not too far off from 45, but looking at how these are scaling, it's probably more likely that there's a better one somewhere between 50 and 55 than between 45 and 50. So it looks like the optimum has moved up a little bit. There's tricks that you can do to keep track of what the best one is. Maybe you could say best angle equals -1, best range equals -1, and then after you find a range here, check if it's better than the best range. If xd -1 is greater than best range, then make best range equal to xd -1, the range of this thing that just happened, and say best angle is equal to the angle that we just simulated that had that. Then at the end, we can print something that explains it. Best angle was angle \n degree sign which traveled X meters. Dot format. Angle is equal to best angle. X is equal to best range, I think I called it. Yeah, so no warnings. So we didn't type a variable that we didn't have. And now we'll get it to just report that rather than us having to read through the data there. So it'll give us a nice summary at the end. Oh, beautiful. Best angle was 50 degrees, which traveled this. And that is the end of the lecture. If you made it all the way through, that's amazing. Thank you for your patience. I hope that you found something that was useful in there, and happy coding.